Okay, welcome back to another video. In this video, I'm going to give some general feedback in relation to a Year 12 General Maths assignment. I was going to do this inside as part of face-to-face teaching and record this at the same time. Fortunately, I'm a little bit under the weather, so I'm actually going to record this ahead of time, and my students will be able to see this sometime in the future. All right, so this is the assignment they've been working on, and a majority of them have handed up drafts. So basically, I'm looking at giving them general feedback here. So I'll now be speaking to them in that sense. Okay, so I'll now switch to my teaching to the students' perspective. All right, so guys. Okay, so thanks for everyone who gave me some drafting. There's some really good work here. There's some things that I was able to highlight and say, okay, fix this, extend on this, you're wrong about this. But there's also some things that I have to kind of either reteach or just show you how to do things or what you might be doing wrong. All right, first of all, mentioned before, please refer to the previous video for the first point. Okay, so there was a number of things that went into the data transformation. So remember, you went and gathered your data using temperature probes. All right, there's a bunch of things that I did with the data. So for example, I went and looked at the top of the data, the head of the data, and I had to find a temperature where they all kind of start together and trend downwards. I also had to sample if they weren't consistent in the readings. So some of the temperature probes were set to every 5 seconds, some were every second. I had to sample the ones that were sampling more. And also, I cut the flow off some of them because some of them read for longer, and it would have made the visualization a little bit more tricky because like some go for longer than others. So there's a bunch of things I did there. There's also a bunch of things that you did with the data. For example, you went and converted the seconds into minutes, and you also subtracted the room temperature from the temperature readings because the thermometers measured temperature, but the way we went and modeled the stuff is using the temperature above room temperature. So, but I think I explained that in more detail in the previous video, so I'm going to ask you to maybe have a watch through that again. Okay. All right, so first of all, there's also some common errors in the conception of what A is. And this comes in, all right, this kind of comes in the explanation of some of the sections near the end of section 1, but also sometimes in the introduction and other areas, there's confusion. Okay, so A is the number of degrees Celsius above room temperature. So you're given this data set. You don't know what room temperature is. Now, I've seen some assignments where people might say, hey, well, it must be boiling because it's a fresh cup of coffee. So thereby the room temperature was 29 degrees, going up to 100 degrees, the boiling point. Well, also remember you've got a cup of flat white, and you're probably adding cold milk. So it might be significantly, it might not be boiling when you stick the thermometer in. So yeah, you don't know. But what you do know is the temperature above room temperature. Okay, so the argument is that I've been seeing there's that you can't use a linear model because linear models they'll go down in a linear pattern and they'll go down to zero. So if I look at my say for example, what's it? Yep, there it is. Okay, so if I turn on my linear model, yeah, you can see this one goes down to 0. All right, and then it goes past 0. Okay, so that's not realistic, is it? Okay, however, well, people are arguing that it is still unrealistic, but what does 0 mean for Y in this case, in particular for A? This is not freezing point of water. This is 0 degrees above room temperature. All right, so yeah, the freezing point would actually be further down, like wherever the room temperature was. So if you go below, all right, if you subtract the room temperature again, you would be around freezing somewhere around here, I'd imagine. So yeah, 0 is the room temperature. Now, it's still unrealistic to get negative A. Why is that? Well, consider it this way: you got a hot cup of coffee. It is losing heat to the environment, which is colder. Heat travels from hot to cold. All right. There's a thing in physics called thermodynamics, in particularly the whole premise about what's happening is heat moves from hot to cold. All right, now there's another concept in temperature called equilibrium. All right, so once you've hit thermal equilibrium, there's no heat flow. So once the environment and the coffee cup are the same temperature, there is no hot and cold to move from one to the other. So therefore, going below 0 in this context is still unrealistic, but for a different reason. So you were right if you said that it shouldn't go below 0, but if you're wrong if you said that would cause the freezing of the coffee cup. No, unless your environment is below freezing, that is not true. So you're right on one point, you're wrong in the other. So I thought I'd clear that up. So A is the temperature above room temperature. All right, now, other key point. Okay, so I'm looking for, when you're doing your work through this stuff, you need to use what we call significant figures, not decimal points. So you would have seen this in some branch of mathematics at some point, but I'll try to explain as best I can with these examples here. All right, so, okay. Now, you notice that I've shown you the exponential model for here. Okay, so you notice you've got, now this is close to 70, it's 69.42. All right, whereas this is 0.9727. They are both examples of 4 significant figures, but they have different decimal places. Now, if you have values that have different scales, so this one's in the tens, whereas this one's starts in the tenths. So this number is always going to be smaller than that number. All right, but okay, when we think about the accuracy of our model, we don't use decimal places, because if I round off the decimal place to the same decimal places, I've gone to that. And you can see the model changed and it got less accurate. I'll turn off the linear one. All right, but if I undo that, there we go. The model is better. That's what's happening with some of your models. You are rounding things to decimal places, and you have one section that is more accurate than the other. And that's going to cause problems. In fact, this is actually the most important part, because this actually tells you how fast it's going down, whereas this kind of tells you where it starts. If this was a little bit off, so say for example I got rid of that, the 0.42, there's only a slight change. All right, whereas if I get rid of, say if I deleted 3 of these, you'll see a dramatic change of this. Yeah, you can see how much that changes, like 0.9. Even if I rounded it up, if I rounded it up to 1, it would stuff it up entirely. If I rounded it to 1, it wouldn't even go down anymore. Yeah, this is really important, this one here. So you need to have more decimal places. This is also true if you look over here, when it comes to what you put over here, because you're going to have to convert this to that. Now, if you look, I might zoom in this a bit, because these are hard to see. All right. So I've got, okay, so significant figures, if their number's bigger than 1, you count all the things in here, unless it's like, unless it has no decimal places and it just has a lot of zeros at the end, you might not count the zeros at the end. All right, but this one has 1, 2, 3, 4, 5 significant figures. Now, I think you need 4, but more is better than less. All right, so this is fine. I'm not going to mark you wrong for a 1 more significant figure. Okay, but if you look here, now, this is now in the, one of the reasons I got you to do minutes is because you have, in seconds, there is way too many leading zeros. It makes things hard, and this is kind of the argument for that. Minutes, at least they start at the hundredths, so if you notice that's units, tenths, 200ths, and 1,000th. Okay, but When it comes to numbers smaller than 1, the zeros at the start don't count towards significant figures because you're not giving any information. You only get information when you get to something that's non-zero. So anything after the leading zeros, once you start with a non-zero digit, you can start counting. So 2, 1. That is only 2 significant figures. Is not enough to make for a good model. You need to include the other ones. Again, go back to the section when I do the graphs in the previous video. I do show you how to make sure that happens. Okay, so you can go back to that other video and show the method. I'm not going to go through the full method how to do that. All right. There's also now when I do the drafting, I try to find as many forms as I can. I missed a lot. I don't know how many I missed. I just realized, okay, well, I missed a few errors here because these are actually inverted, and that's a spelling mistake as well. Temperature is on the y-axis. It should be the temperature above room temperature. Time minutes should be on the x-axis because that's your temperature is going down, and your minutes is increasing. So yeah, that has another fault wrong with it. Okay. Yeah, that's also wrong as well. That's temperature in minutes. So there's a few mistakes here, but this one is correct with the number of significant figures. 51.59. That's 4 significant figures, and minus 0.01749. Okay, so that is 4 significant figures in here, and you're going to need that when you convert it, because we're going to actually convert that form to that form. It's something I'm going to show you. I did show you this in a previous lesson, but I'm going to have to show it to you again because a lot of people aren't doing it right or at all. Okay, excuse me. Okay, so yes, so please start off by doing your initial models with the correct number of significant figures. If you don't do the correct number of significant figures, in part 1 you'll get the wrong answers for things like, okay, so I'm showing you, for example, this is what I'm using to check. I use to check your answers for section 1 when you use the model, because we all did the same data, so we all got the same model. So that you can see my models here, and you can see, yeah, so I rounded my models to 4 significant figures, and you can see my answers for some of these questions. So you got that one up here. I zoom out. I can show you. Yep, there's the first one. There's the first one, and there's the last one. I've got the other ones too, but yeah. Okay, so. Alright, so now I want to, alright, so these ones, that one have to be fixed up before you can do anything. That one we could convert to the other form. Alright, so, alright. Okay, so I'm going to use these ones down here as an example. Alright, also, while I'm doing that, I forgot there's another point I wanted to cover, which is, so convert to that. So I'm also going to show you how to use, Word, okay, we're going to use equations. Okay. Because, yeah, I mean, you can write stuff like this, but this is kind of like, I know I do it, like, but usually I do it so, like, you're pressing the right buttons on your calculator, because you got your calculator, does that sort of stuff. Speaking of which, I should actually load mine up. All right. So, yeah, because it's kind of written in a linear kind of way, but if you're running an equation, so why don't we do something a little bit better? Okay, so let's go to do that. So we're going to do a conversion, but I'm also going to show you it by using equations. So let's use insert. Okay, I've got my thing. Okay, I don't know. I can't see equations. I maybe have to. There we go. I have to make it large enough to get to the equation bar, so I can't do dual screen here. All right. So, all right. Now it will default to the middle, which is kind of annoying at times, but you can just write text before it and it won't do that. All right. But in the meantime, so I'm going to copy down that equation there. So I'm going to write it this way. So y equals. Now, when you're in equations, you notice you get a new, when you insert equation, so I went insert equation. Now, once you're in an equation, so this little box here, you've got a bunch of options there. Okay, so it uses the kind of italic forms of y and x that look kind of the kind of math way of writing those letters, which is kind of neat. But also, you can do things that look very mathy. All right, so let's just do that one. I'm going to round it off to 4 significant figures. Now, that multiplication looks like that X looks like a multiplication sign as opposed to the X that I'll type out in a minute, which is actually the variable X. Now we're going to use a letter E. Actually, for that, I'm going to click script. You can highlight the letter and do this, but if you want to write, okay, E, and I put a minus, and I put 0.02251. And the last thing is, don't forget your variable. Okay, so there you go. You could also write that as A and T. You could change that to that. It doesn't really matter. We know we're talking about X and Y in terms of the X and Y in the graph. So that's fine. It's your model. You can use either. All right. Now, I'm going to convert... okay, so let's not do that. All right. So say, for example, I want to put this part of text. Let's say, so the equation. Just write some text before it, and now it reads as such. Yep, there you go. All right. So we can... Okay, so we're going to convert, I'm going to mention the form, so let me just write another equation. All right, yep. All right, we can convert to, so I want to write the form as this, A times B to the power. So if you've already written that one and you want to write a power, now you don't this isn't entirely necessary because, okay, if you don't want to use this, you can still write power. So say, for example, I want to make this a little bit neater over here. Well, what do I do that? Just use superscripts. So now there is a keyboard shortcut for that, so I can show it you this way. So that's the subscript, sorry. It is Control-Shift plus sign or equal sign. Don't know what it is on the Mac. If you're not too sure, it's... where is it? There's a button shortcut for it, and I've forgotten what it looks like. Oh, there it is. Yeah, it's right there. So yeah, click on that. There you go. Now you got powers. All right. So there you go. Okay. So yep, that's fine. So, but I'm gonna. Let's see. This looks nicer. This is much nicer. And if you got other equation you need to do, you can do it that way. Okay. So the way we're going to do that is by using. Okay. All right, so I'm not going to do another equation. Okay, so the equation is now, B is equal to e to the power of this. E is a number like pi. It is transcendental. It's got a lot of decimal places, like 2.7 something or other. All right, but, okay, the reason why Excel defaults to this is because it's a very easy, I'll just write K for now. All right, so K. All right, so it's the reason why this form is common and why Excel does it is because it is used in calculus, which is stuff that the maths studies people do. All right, so they like their exponentials to be base e because it makes the calculus easy. We like it in the other form because it makes the interpretation easy, and we'll explain that in a minute. All right, but let's just figure this out. So we're just going to write an approximate sign, so that should have been approximate. It doesn't really matter, but you see, now you've got other symbols as well. You can say, that's approximately equal to, because we've rounded stuff off, so it's a little bit more precise. All right, approximately equal to that, which is approximately equal to. Now, okay, so let's bring this over. So you can see I've done an example of that already. Okay, so let's go. Now, how do we do this? Second e to the power of, okay, then you go negative 0.02251. Boom skis. Okay. All right, so that's 0.9777, rounding off at force and figures. 1, 2, 3. Okay, cool. So what does that mean? All right, so that's a B value. I should probably write the equation. Okay, so let's just do that. I'm going to copy paste this, and I'll show you why, because basically all I need to do is, all right. Okay. Okay, so equation is now this. Sorry, I haven't actually changed anything, have I? All right, so now I'm going to replace my E with 0.9777, and I'm going to get rid of just everything except for the X. Okay, those two equations are the same. If you don't believe it, put them both into Desmos, plot them, see if they overlap. And they should. Okay, if you've done them right, they should. If there's a problem, let me know. Okay, so we got the equation now. All right, so what does B mean? Okay, it is the rate of change. I was playing a bit better than that. Okay, in this context, in this context, 0.9777 is the proportion of temperature kept per minute. Okay, so all right, so what that so in other words, 97.77% of temperature 1 minute, or probably the better way to describe it is this: if you subtract that from 100%, 2.23% temperature is lost each minute. Okay. So that's a way to think about it. And if you do this, you can actually go, okay, because one of the major things that very few people are doing is you're not using your models that you find using all these graphs to do anything. You're going back to the final temperature and just saying, well, that one had a lower temperature, that one, so thereby. Well, what about the overall patterns? Like, yeah, the idea of finding these models is showing this overall pattern. Some people are commenting on like kind of strange behaviors in the data and things of that nature, which is kind of cool. But that's all good stuff. But you're not doing anything to use anything. So I'm going to write another equation. Okay, so let's go. Okay, this one was no. Sorry, we're looking at these ones. All right, so we've got aluminium can. Okay, so AL can. So we're going to take these models. Okay. Okay, and then we're going to look. This is from another person's work. Okay, foam cup. So this is excellent. Degrees of room temperature, time passed since water poured, minutes. Technically, there's a little bit of finagling with the data. I'll let it pass. Close enough. It's a really good graph. Yeah, and I like the fact I can see the model and the data very well here. That's well done. But yeah, you can't name names in these videos, unfortunately, so that you can pat yourself on the head if you recognize your graphs. Okay, so aluminium can and foam cup. Foam cup. Okay, so let's just go with, all right, so I'm just going to copy this again, but we're going to delete this. So that's actually, this one is 4218. Okay, and I have to convert that one as well. So let's go down here and pull my calculator back out. All right, let's do another conversion. All right, so I can just copy this. Okay, I'm going to change that to, go across, okay, 5, 7, 3, okay, boom skis. All right, so, okay, so this one's actually losing more. Okay, interesting. I would have, okay. So, okay, oops, lost it. Okay. 4, 5, 4, 6 if I round that to 4 figures. So the next two digits are 4 and 6. Okay, so there's our two models. All right, so then I can make a contrast and say this, and then each minute. Okay, the aluminium can loses. Okay, what did we say? 2.323% temperature. Oops, 3% temperature. From previous minute. Because we're basically losing. If you lose 2%, so say if you started at like 100 degrees, you'd be down to like 98, but then you lose 2%, 2.23% of that, and you're kind of losing less, which is why the curve flattens out to almost horizontal, because you just keep losing. Like technically you never really reach the room temperature if the model holds true. But eventually it becomes a rounding error. Like you can never measure that close to the room temperature, the difference between them. So yeah, doesn't matter. Okay, so all right, from previous, according to the model anyway. Um, but and the foam cup loses 2 point. If I rearrange that now, if you just times that, take this value here, times it by 100. Times it by 100. Put as percentage. Subtract it from 100 to work out how much heat is lost. You'll end up with 2.54%. Trust me on this. Well, check for yourself by all means. Okay, but yeah, see this one's losing more because this is a slightly smaller number. So there, you've drawn a comparison. So you've done at least a few of these. So you should be able to see, you should be able to tell, use your models in this sort of way to look at the rates of change, because now you can see how fast it's going. Whereas if you just use the endpoints, it's kind of like you're using a less sophisticated way of comparison. You've made these models. You need to be using them in your explanation of what's the difference between the different cup types. Unfortunately, I haven't seen a lot of assignment drafts in terms of the rooms, so I don't have too much to say about that, but people can come and talk to me at a later date about that. All right, I think that's everything I wanted to cover. Okay, so I'm going to leave the video here. All right, thanks, guys.